Hello, Math 2 Extended. This is Mrs. Bricky, and this video is for Unit 2, Lesson 4. We're going to be doing operations with complex numbers. So a complex number is a number that can be written in the form of a real number plus an imaginary number. So maybe, for example, 3 plus 5i or 2 minus 7i. A complex number is in standard form when the real part comes first and the imaginary part comes second, and then also both parts should be simplified. So here's some examples of some different complex numbers. All of these are complex numbers. So we want to circle the ones that are in standard form, which is a plus bi. And anything that is not in standard form, we're going to simplify and write it in standard form. So this first one has real part 7 plus imaginary part negative 6i. So this is in standard form. Now, please note, if b is a negative number, it will look like a minus bi, but that's still in standard form. So let's go across the rows. So 1/2 minus 5/3 I. So we've got the real number 1/2 plus the imaginary number negative 5/3 I. So that one is also in standard form. Negative 19. This is a complex number. And it is in standard form and it is simplified, so that's good to go. It's the same as the complex number negative 19 plus 0i. All real numbers are complex numbers with a 0 imaginary part. So that is in simplest form there. It just has a 0 imaginary part. If a complex number has a 0 imaginary part, we do want to not show it. So this is the same as the number negative 8. That is a complex number in standard form. All right, this next row has negative I minus 3i. So if we can combine those two, that's a negative 4i. And so that would be its simplest form. It's the real part is 0, but if it has a 0 real part, we just don't write it. So we just write negative 4i. Negative 9 plus I, real part comes first, imaginary part comes second. That one's good. 4i plus 11. This one is definitely not in standard form. The real part of 11 should come first. The imaginary part, 4i, should come second. Okay, this next one is 5 plus 4i plus 6. So we want the real part first and the imaginary part second. Well, these two can combine to an 11. So 11 plus 4i, those are actually the same number. All right, 0 minus 2i, well, we don't, if we're going to have it in simplest form, we don't need that 0 there, so this would be just negative 2i. 20i, yep, that is in standard form. The real part is 0, but if we have a 0 as our real part, we don't need to write it, so 20i is the simplest form. 1 minus 12i, and that number is squared. Now, the complex number system is a closed number system. That means if we multiply two complex numbers or add two complex numbers or divide two complex numbers, we would get an answer that is a complex number. This is a complex number. It is the number negative 143 minus 24i in standard form. So this is a complex number, but it is not in standard form in this form. In standard form, which I'm going to show you how to do in a minute, it would be negative 143 minus 24i. Okay, this last one, real part 7, imaginary part is root 2i. This is in simplest form. It's okay that it's root 2 after the I. It's also okay if you write it like this, but it just is so easy to have that turn out to look like the I is under the root. So standard practice would be to put the I in front of the root so that we don't have any confusion about whether the I is under the root or not. So that is considered standard form. Okay, so all of our answers as we start doing operations with complex numbers, all of our answers we want to report in standard form. Real part first, imaginary part second. Okay, so the complex number system is a number system that includes all real numbers and all imaginary numbers and all numbers that have both a real and an imaginary part. So anytime you're talking about a real number, that is a complex number that has a zero imaginary part. And anytime you're talking about a pure imaginary number, that is a complex number that has a zero real part. But these are all in the family of the complex numbers. Okay, we're going to do some operations with complex numbers now. We're going to add complex numbers, subtract complex numbers, multiply complex numbers, and then finally divide complex numbers. So our first problem, we've got a 2 plus a 15i plus an 18 plus a 4i. Addition of complex numbers just follows the same rules as polynomials. We combine like terms, but what that means in the context of complex numbers is that we look for the real parts and combine them with the other real parts. So in this case, we've got a 2 and an 18, so that's a real part of 20. And then we combine the imaginary parts with other imaginary parts, so we get 20 plus 19i. And this answer is in standard form. I have the real part 20 before the imaginary part 19i. They often will be shown in parentheses like this. We have the complex number 3 plus I, and we're adding the complex number -7 minus 5i. The parentheses don't mean multiplication. The parentheses are just to show that we have two separate complex numbers that we're adding together. We still just combine the real parts and the imaginary parts when we're adding. So our real part would be -4. That comes from those two. And then the imaginary part, we've got 1i and -5i that we want to add together. So that would be -4i. So -4 minus 4i. And those two parts can't combine because one of them is the real part and one of them is the imaginary part. When we're subtracting, just be mindful that the subtraction applies to both the real and imaginary parts of the number being subtracted, and always, of course, be careful with your negatives. I like to use a rewrite strategy. So I have a 5 minus I, and this is subtracting a -7. So that's adding a 7 and subtracting subtracting a 2i. So here is my list of terms. So our real part adds up to 12, and our imaginary part combines to be -3i. And we'll use that rewrite strategy again. We have 6 minus 8i. I'm subtracting a -1, so that's the same as adding 1, and I'm subtracting a -6i, so that's the same as adding 6i. So we end up with a real part of 7, and our imaginary part, when we combine those two imaginary parts together, we get -2i. So we are just performing an operation with a complex number here, and we're getting an answer that is a complex number. Please note, when you're solving an equation, and we take square roots, and we put plus or minus symbols, when we're doing that, we are just getting two complex answers. So when we're solving an equation and we have 7 plus and minus 2i, it really means that the two complex numbers that are solutions are 7 plus 2i and 7 minus 2i. These are each individual complex numbers. So this solution, or this difference that we found from subtracting, it's this number that we found. When we're solving equations, we have two answers, two complex number answers. So we don't have a plus or minus here or anything, but when we're solving, the plus and the minus are just two separate numbers. So I just want to emphasize that. With solving, you have two answers, two complex answers. This is just adding and subtracting. Okay. We're going to switch to multiplying now. When we multiply imaginary numbers or complex numbers, it follows the same rules as monomials, but simplifying your answer is slightly different. We need to report our answer as a complex number in standard form. This is a closed number system, so if we multiply two complex numbers, we will get an answer that is a complex number, but we need to make sure we report our answer in standard form. Your answer can't have any powers of I higher than just an I with a power of 1. For example, you won't have a final answer that has an I squared in it. So let's try a couple of examples, and as we have an I squared pop up, we'll talk about how to deal with it. So our first example is -3 multiplied by 6i, and that is just -18i, and that's my answer. So that was a real number multiplied by imaginary number. What if we multiply two imaginary numbers together? Well, I've got 5i, and I'm multiplying by -7i, and I get -35i squared. Well, we can't report any answers that have a higher power of I than just 1, so we can't leave our answer in terms of I squared like this. We have to remember that I squared is the same as -1. So if I have -35 multiplied by I squared, that's the same as a -35 multiplied by a -1, because I squared is -1. And this is a multiplication relationship right there, so we are timesing by that -1, and so our answer is 35, positive 35. 2i squared is 2i multiplied by another 2i, so that is 4i squared. We don't want to leave that power of 2 on our I, so we replace the I squared with a -1, because I squared is exactly equal to -1. That's a multiplying relationship, so we have -4 as our answer. If we have a complex number like 5 minus 2i that we want to multiply by 4, or a 2i times by a 3 plus 7i, we're going to have to use distributing. And in a second, we're even going to be multiplying two complex numbers like these together. So we'll have to do a lot of distributing. So we need to distribute these and perform the multiplication, and then simplify our answer and put it into standard form. So 4 multiplied by 5 gives us 20, real number. And then 4 multiplied by -2i gives us -8i. And in this case, I've got a real part and an imaginary part, and I'm done. That's already in standard form. But now we're going to multiply by 2i. So 2i multiplied by 3 gives us 6i. 2i multiplied by 7i gives us 14i squared. Now, I don't want to leave my answer like this because this is not in standard form, and we know that that I squared is equal to -1. So this is the same as 6i plus 14 multiplied by -1. So that's a -14 real part and a 6i imaginary part. You might start to notice that the effect of having that I squared is essentially that it becomes a real number with a sign change, because I squared is just -1, so it just multiplies by a negative. Okay, let's try these two. So we're going to first distribute the 5. 5 times 6 is 30. 5 times -4i is -20i. We finished distributing the 5. Now we need to distribute the 2i, the second term. So 2i times 6 is 12i. And 2i times -4i is -8i squared. So the 30 is a real part for sure. And then these two terms are both imaginary. Negative 20i plus 12i is negative 8i. And then this guy over on the end, negative 8i squared, well, that's the same as a negative 8 multiplied by a negative 1. So that's a positive 8. So these two real parts can combine together, the 30 and the positive 8. So we have a real part of 38 and an imaginary part of 8i. Let's try another one. 3 multiplied by 7 gives us 21. 3 multiplied by negative 5i gives us negative 15i. Negative I multiplied by 7 gives us negative 7i. And negative I multiplied by negative 5i gives us positive 5i squared. So we have these two imaginary parts right here, negative 5 and negative 7i. So those two combine to give us a negative 22i. And then this guy over here, we can replace that I squared with a negative 1. So this is the same as negative 5. So we've got a positive 21 and a negative 5, and that gives us 16. So our answer is 16 minus 22i. Okay, what does it mean to square? Well, remember, squaring just means to take something and multiply it by itself. So we want to square 2 plus 3i, so that means we need to multiply a 2 plus 3i by itself. We get 4. We get a positive 6i. Now we switch to distributing the 3i, so we get another positive 6i. And then we have a positive 9i squared. So definitely these two are going to combine to give us 12i. That I squared with that 9 is a multiplier of negative 1. So we have a 9 multiplied by a negative 1. That's negative 9. And we also have 4. So we have a 4 and we have a negative 9. And that gives us negative 5 plus 12i. So real part first, imaginary part second. Okay, now we have 5i that is being squared, and we're multiplying by a 7i to the third power. Well, a 5i squared is the same as 25i squared, and that's the same as negative 25. And then I need to multiply that by 7i to the third power. Well, I to the third power is just like I times I times I. That's third power. So we could think of these two as an I squared, and then we just have this extra I. So this is like timesing by negative 7i. So this I squared in the middle becomes a negative 1, and so this is negative 7i. And so now if we finish multiplying, we get 175i. Okay, fill in the blank to make a true statement. So when you're doing problems like these, just like with polynomials, you focus on like terms. So I'm going to focus on the real numbers. Real number, real number. Something minus 15 gives me 7. Well, that something is 22. And now switching to focus on the imaginary part. Whoops, sorry. We have negative 3i minus something gives us negative 12. So we focus on the imaginary part. Well, negative 3 minus 9 gives us negative 12. Please note the minus is here. We don't need a negative with the 9 because of the minus symbol. Okay, for the video, I'm gonna skip that. If you want to stop the video for a minute and practice a couple before we move on to dividing, that's probably a great idea. Okay, dividing complex numbers can be a little bit tricky. You just have to get the hang of it. It's not like super hard, but there's definitely a procedure to it that you need to follow, and it is a little bit more complicated than multiplying or adding. So, in order to divide complex numbers, we'll be using something that is called the conjugate. So, a complex conjugate, every complex number has a complex conjugate, and the complex conjugate is a complex number that looks almost the same. For a plus bi, the conjugate is a minus bi. So the sign of the imaginary part is the opposite. So nothing else about it changes. It just switches the sign only of the imaginary part. So the complex conjugate for 4 minus 7i is 4 plus 7i. The conjugate for negative 5 plus 6i is negative 5 minus 6i. And you'll notice that the real part stays exactly the same. 4, 4, negative 5, negative 5. The part that changes is the sign of the imaginary part. So this one would be 1/2 minus 3/4 I. This next one would be negative 9 plus I. And this last one, the conjugate would technically be negative 7i, because the imaginary part is the part that changes sign. So maybe you're thinking to yourself, how in the world could the conjugate be helpful? Well, the reason complex conjugates are helpful is that when we multiply them together, their product is a real number. 4 times 4 is 16. 4 times 7i is 28i. Now I switch to distributing the negative 7. Negative 7i times by 4 is negative 28i. And negative 7i multiplied by positive 7i is negative 49i squared. And maybe you're thinking, man, that doesn't look like a real number, but it is, because look, the 28i and the negative 28i, they cancel out. So there's no i's on those two middle terms anymore. They're gone. They added up to 0. And then this guy right here, that's an I squared, which is the same as the real number negative 1. So this actually is 16 plus, oh, sorry, my computer sometimes can't process fast enough. 16 plus 49. That's a real number. That's the real number, 65. And it will always be the case that when you multiply a complex number by its complex conjugate, you will get a real number. And you can see it if we even just use an a and a b. A times a is a squared. A times negative bi is negative a bi. Bi times a is positive a bi. And bi multiplied by negative bi is negative b squared I squared. So again, you can see that negative abi and the positive abi cancel each other out. They add up to 0. So then I have an a squared minus a b squared I squared, but that I squared is the same as negative 1. So we end up with an a squared plus a b squared. So not only is the product of complex conjugates a real number, but it's always a positive number. So now you're thinking to yourself, perhaps, well, how can that help us divide? Well, dividing complex numbers is a little bit weird. So our problems are going to look like this. And the way that we're going to be able to divide is to multiply by a fancy number 1. We're going to change the form of the fraction without changing the value of the fraction. And if we carefully select what that fancy number 1 is, it will help us simplify this problem by making that denominator a real number. So before we start, I just want to show you this little example. If I have an 8 plus a 6i and I want to divide it by 4, I absolutely can do that. It's 8 divided by 4, which is 2, plus 6 divided by 4, 3 halves I. So when I divide by a real number, I get this complex number result that has a real part of 2 and then an imaginary part of 3 halves I. We are going to often have fractions in our division answers. Our answers are often going to look something like this. So what our goal is, when we have it in this form, when we have a problem like a plus bi divided by c plus di, our goal is to turn it into something that looks like this, and then we can just divide by that real number to get our answer. So it also has some parallels between if I have a fraction 1/2 and I want to write it an equivalent fraction in a different form, I could multiply by 4 divided by 4 to get 4/8. And we know that 1/2 is the same as 4/8. They're just in a different form. And when you do something like that to a fraction, you're really just multiplying by 1. That's why they're equivalent, is because you're taking that number 1/2 and you're multiplying it by a fancy number 1. And so you get an equivalent fraction that's just in a different form. So here we go. I know that's a lot, but it's helpful in the long run to help you understand what's happening. So we need to simplify this expression. We're dividing two complex numbers. We know our answer is going to be a complex number. Let's find it. Well, I'm going to take this fraction and I am going to multiply it by a super fancy number 1. That's going to preserve its value and just change its form. And what we want to do is choose to multiply by the fraction that is the conjugate over the conjugate. 1 plus 4i divided by 1 plus 4i. If I multiply by 1 plus 4i divided by 1 plus 4i, it's the same as multiplying by 1. So my result is going to be equivalent to that original fraction. So we need to now multiply out the top and multiply out the bottom. So 7 plus 5i multiplied by 1 plus 4i, we get a 7 plus a 28i, and we get a 5i plus a 20i squared. That's the numerator, multiplying out the numerator. And I'm just going to finish simplifying the numerator. The 28i and the 5i combine to give me 33i. And then the real part is the 7 combining with this real number -20. So that, remember that I squared is a -1, so this is a -20. And then 7 plus -20 is -13. So my numerator is -13 plus 33i. Now I'm going to multiply out the denominator. The denominator is 1 plus 4i times 1 minus 4i. So if I times that together, 1 times 1 is 1. 1 times 4i is 4i. Negative 4i times 1 is negative 4i. And then that I is really bad. And then we have a negative 16i squared. Well, those 4 i's are opposites. They add up to 0. They cancel out. And then I have the number 1, and I have the real number 16, because that is just a -1. So that ends up being a real number, positive 16. So my denominator is 17 when I combine those two numbers together. So this is my complex number answer. The real part, sorry, my computer sometimes struggles when I'm making videos. The processor is just like having troubles. The real part is -13/17, and the imaginary part is positive 33/17 I. So you can see, this real part right here and the imaginary part right here. And that 17, that 17 is just dividing both parts. It's dividing both terms in that complex number. So this is our answer. If I have the number 7 plus 5i and I'm dividing by the number 1 minus 4i, my answer is -13/17 plus 33/17 I. Okay, let's see. We've got a 2 minus a 3i, and we're dividing it by a 1 plus I. So the way that we perform that division is by multiplying by the complex conjugate. So the complex conjugate is 1 minus I. And we're multiplying the same on the numerator and the denominator because that is just a fancy number 1 that we're multiplying by. So in our numerator, we now have 2 we have a -2i, we have a -3i, and then we have a positive 3i squared. That positive 3i squared comes from those two terms multiplying together. So that's our numerator. If we simplify that numerator, our real part is -1 and our imaginary part is -5i. The -1 is the combination of the 2 and the -3. A positive 3i squared is the same as a -3. In the denominator, we have a 1. We have a -I, we have a positive I, and we have a -I squared. Well, these two do cancel out to add to 0. This is a tricky one. Sometimes the people want the denominator to be 0, but this is 1 minus I squared. That's the same as 1 minus -1. So that denominator is actually the number 2. So our division result, our real part is -1/2, and our imaginary part is -5/2 I. That's our answer. Okay, last problem. We have 6 divided by 2i. Absolutely, you can reduce this if you want to 3 divided by I. I want to show you how to do it without noticing that it reduces, but if you do notice it reduces, you'll get the same answer. So we want to multiply the top and the bottom by the conjugate. That's -2i. Oh, my computer is struggling so much. Sorry. So if we multiply the top by -2i, we have a -12i. And if we multiply the bottom by -2i, we get -4i squared. Well, that I squared is just -1, so this becomes -12i divided by a positive 4, because -4 multiplied by -1 is positive 4. So our final answer would be -3i. And you could get that by reducing first as well. You end up with a -3i divided by, oh, that looks like a minus, sorry. A -3i divided by a -I squared, but -I squared is the same as a positive 1, so we end up with -3i as our answer either way. Okay, sorry. Oh my gosh, the computer struggle today is real. Okay, so -3i is the answer. Either way you do it. Wow. Okay, I think my computer is dying. Okay, so crazy video. That's it. So today's big ideas are complex number standard form should be a plus bi. When you add or multiply or divide two complex numbers, the result is also a complex number. And If you have any questions or need help with your assignment, please let your teacher know. Thanks so much.